going to complete the discussion on planning graphs and negative interactions, and then sort of either today towards the end or next class we will basically kind of glide into the landmark heuristics. They're very well connected actually. It turns out, actually in fact, those of you who have looked at the tutorial slides, if you open the tutorial slides I sent, there is in fact, I was asking you guys to think about what may be the connection between landmark heuristics and planning graph heuristics, and it turns out that if you look at the tutorial slides, there is a method due to Zhu and Given, which actually just directly computes landmarks by propagation over planning graphs. Okay, we will discuss that. In fact, we will start talking about notion of propagation over planning graphs sometime today, because you are actually propagating achievability right now. When we are making planning graph, it's sort of you could actually think of planning graph as being constructed incrementally, or you can assume as if planning graph exists and you are just sort of propagating some information over the edges of the planning graph. And what we have done till now essentially is propagating achievability. Okay, so only the things in the initial state have the label true. Okay, and in essence you are propagating the true label upwards, outwards. Okay, whenever you have preconditions, you take the conjunction of the preconditions to get the label for the action. And whenever you have a proposition, you take the disjunction of the labels of its incoming links, the action links, to get its label. Now remember that in this particular case, labels are just true and false. Okay, and so in some sense, the idea of constructing planning graph along with the label propagation is that those actions which will wind up having false label, or those propositions which will wind up having false label, don't even come into the planning graph. Okay, that's why you never see false labels. But this view itself is a very powerful view. Act as if planning graph existed and you are propagating all sorts of information over it. Okay, so the information that I was propagating is, if the planning graph existed, I was propagating the information of true, false, all the initial state literals have true, and then whenever there is an action, of course it will have a true, and whenever there is a condition, then it will have a true. So now in planning graph itself, the one that we construct from scratch is really the subgraph of the planning graph that has the true label. Think about it that way. Okay, universal planning graph will have everybody in the planning graph, but now we are only constructing the part of the planning graph that actually has the label true. Now one of the interesting things about this view, and again I'm jumping ahead, I'm abusing the fact that this is a grad class, and in fact I'm generally happy with the reviews that people wrote, so I'm assuming I can abuse you even further by jumping around. So one interesting thing that we'll be discussing today is mutexes, right? One idea would be, you can think of, in fact, the Lin and Zhu, from the Zhu and Given's paper, original paper that I'll probably send you a copy of later on. It actually also talks about this idea of quadratic planning graphs. What's a quadratic planning graph? In a planning graph, normally you only have a vertex for each action, each proposition. And the one that you incrementally construct, you don't even put in propositions and actions that have false label. Okay? Okay. Now, in a quadratic planning graph, in addition to propositions, individual propositions, you also have vertices for proposition pairs. A and B, B and C, C and D, D and A, all of them together. Okay, so the proposition length lists are much larger. Now the interesting thing is, even though we will discuss mutexes in the old-fashioned way in today's class, you can actually think of mutex propagation as this kind of true-false label propagation over those pairs. A very powerful unifying theme. Okay, and in fact we will see this notion of propagation will also help, of course, in computing landmarks, that in their case, and we'll also see this notion of propagation helps in cost propagation over planning graphs. So if the actions have non-uniform cost, you can propagate the costs over planning graphs. You can propagate probabilities over planning graphs. You can propagate possible worlds information over planning graphs. So once you get into the habit of propagating, you can start propagating lots of other things. Okay. So I want you to kind of keep in the back of your head this idea of propagation. The exact example of which in today's class will be cost propagation. But if we go well in speed, either today or next class, we will be actually looking at landmark computation as a propagation heuristic, as a propagation procedure, which is what Zhu and Give and do. Okay, fine. So, so that's actually, this also kind of says that all these things are kind of connected. Planning graphs are connected to landmarks, landmarks are connected to, and both of them are connected to this notion of relaxed problems and solving the relaxed problems. Okay. Any questions before I go forward? Okay, so we talked about relaxed plan heuristics, which are basically subgraphs over the planning graph, normal planning graph, not the quadratic planning graph, as I mentioned here, where you're looking for the subgraph of the planning graph that supports all the goals. And you're interested actually in finding the cheapest such plan, really speaking, but finding the cheapest such subgraph would require branch and bound, and it can be shown to be NP-hard. However, as I mentioned last class for a long time, one advantage of finding, so instead you use greedy methods. Now, so greedy methods are actually non-backtrackable, in the sense so the idea in the case of finding relaxed plans over the relaxed planning graph, that means planning graph without mutexes, has this property that once you commit actions in this layer, you will then get the precondition in this layer, which can then be supported in the next layer, which can be supported in the next layer, and so on. You may decide which choice to use in each layer, okay, and that you're doing it greedily. Look for the cheapest way, locally cheapest way, okay, and so it won't be a globally optimal way. But you will never be forced, for feasibility reasons, to backtrack from one level to previous level. Okay, and that's a big advantage. Okay, so in the case of, so normally you don't get this, that optimality is NP complete, but feasibility is polynomial. Sometimes you get it, sometimes you don't. In this particular case, for the relaxed plans over planning graphs without mutexes, optimality is NP complete, feasibility is polynomial, because you can do a greedy search. Whereas in the case of planning graph with mutual exclusion informations, you would be finding bounded length plans. That means you're looking for a subgraph of this planning graph that is actually consistent. That's like finding a bounded length plan, a plan of length greater than or equal to this size, less than or equal to this size. That turns out to be NP-hard whichever way, whether you look for optimal or feasible. Okay, just to make sure that we are on the same page, remember I said planning is p-space complete. And I just now said that once you put mutexes in, finding the feasible plans, which turns out to be a way of doing actually planning, is only NP-hard. It's actually an NP complete. So what gives? Why did I say, why was it that the planning is p-space complete, and yet finding a feasible subgraph or optimal subgraph of planning graph with mutexes thrown in, which I will prove to you, that you already understood, that's how graph plan works. So why is it that that's NP complete, not p-space complete? Yes?
Is it because the planning graph can be exponentially long?
Exactly. Basically, all I said is the length, given a planning graph of length k, the cost of finding a subgraph of that planning graph, which is a feasible plan. That's just a decision problem saying, is there a plan of length k for this problem? that decision problem is in fact NP complete. Okay, the problem of is there a plan for this problem, that can be p-space complete, because the only plan that does exist is exponentially long. Okay, so in fact many people, despite the fact that you have this p-space completeness that holds, because again the way to remember p-space completeness is what? Is to realize that Tower of Hanoi can be written up in big DL, right? Okay. So anyway, so that's the deal regarding the NP completeness that we'll get to in a minute. But here itself, feasibility is greedy, and optimal is optimal is NP hard. Now here's an interesting question. One thing that in the planning community people are kind of split into people who are interested in finding optimal plans and people who are interested in finding feasible plans. That means satisficing. Now the interesting thing, of course, is operations research people don't even have this fancy name called satisficing, because they always assume you have to optimize. Okay, and in fact AI does have the word satisficing, and the only Nobel Prize that ever was given to anybody in AI was given to somebody who coined that name. Who is that person?
Herbert Simon.
Herbert Simon. Herbert Simon actually he coined the word satisficing to essentially talk about human decision making. I mean, he was an organizational psychologist, and he was looking at Milwaukee Municipal Corporation and looked at how they make the decisions and so on, and he did a case study, and he essentially then came up with this conclusion, which I guess all of us would have come up with, that basically most human decision making is satisficing rather than optimizing. Okay, so that means you'll at least make sure that all the constraints are satisfied. This is sort of like finding a subgraph that will be a plan rather than finding the optimal subgraph. Okay. Anyway, so in the case of planning, there are people working on feasible and people working on optimal, and in the IPC, in the planning competition, there are actually two different tracks. One called satisficing track, where you won't get thrown out if you don't get optimal. It's just that you'll get more points if you get better and better solutions. Okay? Whereas on this side, for every problem there is only an optimal solution. Given an objective, there is only one particular optimal value for that objective that is achievable. Okay? So on this side, you really don't care about whether or not, so nobody looks at your plan. Basically by construction, the plan has to be optimal. Okay, so if you ever give out a plan that's not optimal, then you would be just banished from the competition forever, because that means, you once said it's optimal when it wasn't. And you remember, those of you who thought of, I may have said this in 471 if you took it, but otherwise you also know this, that correctness is a local property. If somebody gives you a plan and says it's correct, you can check, you can call their bluff and check by just looking at the plan. Optimality, on the other hand, in most general cases, is a global property. If I tell you it's optimal, there's no way you can call my bluff other than to look at the entire search space yourself. This is why we require people to provide a proof beforehand that it's optimal. And if your proof is buggy and you get caught once, then you should be thrown out of the competition for like 10 years, as far as I'm concerned. Because anybody can say it's optimal and nobody knows how to check whether it's optimal or not. Right? Because nobody can easily check it. So anyway, one of the interesting questions then is when you are talking about heuristics, if you are using the heuristics on this side, you really don't care whether or not they are admissible. You just want them to be good enough informed. So in fact, the definition of informed normally is done only with respect to admissible heuristics. Okay? But we will assume that we can let's say that's the H star. Okay, we'll assume that informedness essentially is how close you are coming to H star, even though once in a while you are actually crossing it. Admissibility, on the other hand, is that you never ever crossed it. Okay, I understand the technical definition of informedness in Intro to AI is that you don't even consider this. This is an inadmissible heuristic, so you don't talk about its informedness at all. But in general, in practice, you know, a heuristic, most heuristics are inadmissible, the ones that are used in the satisficing side. And what you want is the ones that are actually coming closer to H star, so that you can cut down the search. Okay, that's fine. So obviously, relaxed plan heuristic can be used there. Obviously, you know, compared to what's this? This is H11 and this is H-sum. I mean, these are two examples, right? One of which H11 works well, one which H-sum works well, and relaxed plan heuristic will work well in both of these. So you can imagine it being a better heuristic than this for satisficing. For optimizing, on the other hand, H-level is an admissible heuristic. H-relax normally is not admissible because nobody actually spends time finding the optimal relaxed plan. If they do not find the optimal relaxed plan, then their heuristic is no longer admissible and they essentially can't be sure. There are a few people who actually try working on the optimal relaxed plan construction and trying to amortize the relaxed plan construction over multiple you know, times and so on. But almost there is almost a like a division between the satisficing planners and the optimizing planners. And the optimizing planners are significantly lower in efficiency. You know, they typically solve much smaller problems. Okay, with guarantees of optimality. Okay, so again, relaxed plan heuristic is not admissible, at least the way that's normally used, because they just look for feasible relaxed plans. You can make it admissible by doing branch and bound on top of this. Okay. So having said relaxed plans, actually, since this is more or less what most planners up until I guess last year were pretty much using, and even the one that won the competition, Llama, that won the competition last year, was actually using planning graph heuristic plus landmark heuristic, okay, which unfortunately is not explained clearly in the 2008 paper, but if you take time and reading the journal paper, it is explained that they wind up using two different heuristics in parallel. They do what's called a multi-heuristic search. And that actually brings up to a different point altogether, which is when an engineered artifact works, who gets the credit? And when the engineered artifact fails, who gets the blame? Okay? If FF wins the competition, who gets the credit? One of the interesting things we'll notice is, sort of motherhood and apple pie kind of a thing. Why does America work? Because of motherhood and apple pie. Because we just decided those are the easy things to give credit to. Okay? It could also be because people don't go to sleep. French actually have vacations, Americans don't have, and they just keep working, and that's why it works. And that's a much more depressing explanation as to why America works, right? And so you go for the more, happy explanations, short explanations. And one of the interesting things we'll see, again, this is sort of a, digression, but it's important for you to understand this, is FF works because of 18 different pieces of things that they do in their code. Okay? And yet they wind up giving credit for FF's working to the relaxed plan heuristic. And those of you who actually take the FF heuristic, and this is not just FF, this is, as I said, America and motherhood and apple pie and stock market. At the end of every day, there is a crystal clear explanation as to why stock market behaved exactly that way. And they don't say it is because the sum of the stocks comprising S&P, 500 different stocks, some went up, some went down, weighted average was exactly, happens to be equal to 10.47. That's the explanation. But that's boring explanation because you don't feel as if you understood anything. Instead, you just make up a random explanation. Like, for example, the factory orders went down in Beijing, and that's the reason. Now, is that really the reason? That same thing happened day before yesterday too, but stock market didn't go down, right? Right. So now the interesting thing I'm trying to make is that when you learn from engineered artifacts, you have to keep your skepticism antlers, on high alert as to what the author is saying and what the real reason is why something worked. Okay. Oftentimes for engineered artifacts, it's not very easy to say that one little thing made all the difference. Like, for example, why is Brooklyn Bridge able to survive this long? while other bridges keep collapsing. Okay, there is no single reason. And we would like to give a nice little reason so that people will sort of, fall for it, but there is no obvious single reason. Now coming back to FF, it turns out that we'll see today that it does use relaxed plan heuristic. And in the original paper, he basically pushed that in the in the jail paper. He put all his weight behind relaxed plan heuristic and said that's the reason. That's the Beijing factory orders being down. That explains why FF worked well. And then he also had bunches of other sections saying, by the way, I do something called enforced hill climbing, which is completely different from A-star search in some really crucial ways. And I also use something called helpful actions heuristic, which is it's a non-completeness preserving branching reduction heuristic. It reduces the amount of branching. Okay, and plus, by the way, he also does pretty smart grounding process. And if any of those die, then you won't know the difference as to whether or not it's using relaxed plan heuristic, because it will still die. It will be like the fourth in the competition. Okay, so it's important. In some sense, one of the things that happened in the community is for the longest time, and in fact today's class I'll try to say relaxed plan heuristic is a great thing, we should understand that. But increasing, and that's what happened in the community too, but increasingly people are realizing that the search, that enforced hill climbing was just as important. Helpful actions heuristic was just as important. Okay, now if you read Lama journal paper, by the time of Lama, in fact, they are little less into just identifying one single thing. If you read the entire paper, they will actually have one section for multi-heuristic search. In essence, what they wind up doing is they keep two different open lists for the A-star search. One sorted by landmark heuristic, one sorted by relaxed plan heuristic. Okay, and then they keep picking, sometimes the top node from this, sometimes the top node from this. Anytime a node is picked from any of these queues, its children are introduced into both the queues. And their heuristic value is computed for that particular, and so if you are in this, then you'll get the landmark heuristic for yourself, and if you are in this, you'll get the relaxed plan heuristic. That's one idea that seems to make a big difference. Okay, not a very sexy idea, but it's an important idea. Another idea that they wind up doing, and all of these are like 471 A-star search kind of stuff, is, in A-star search, when do you compute the heuristic for a node? As soon as the node is put on the open list, before you put it on the open list, you'll compute the heuristic and compute the F value for the node and put it in, because you're supposed to re-sort the open list so that the best F value will be in the front. Now what happens in planning is you generate a lot more search nodes than you ever expand. Remember, in search there are generation of nodes, which means they ever got onto the open list, and the expanded, that means they ever got picked off from the open list and were subjected to child generation function. In the normal classical A-star search, we tend to assume that all the hard work is in the expansion, and there are lots and lots of expansions going on. Okay, but in planning, many domains, it so happens, basically because most of those analyses are based on tree-shaped search spaces. In a graph-shaped search space, it tends to happen that you will have many more nodes that are generated than are expanded. And remember, one of the big things I made is in the old days, people used to go for heuristics which are cheap to compute. Remember this picture? And people are computing heuristics here. Now we are so much smarter, we are computing costly heuristics in the planning graph side. And if you read the landmarks paper, that's even costlier than the planning graph heuristic. At some point of time, you must be thinking, if it's a small enough planning problem, I'd be wasting more time computing the heuristic than solving the problem. Which is true, actually. But for a large enough problem, it makes a big difference. Okay, now the question is, since the heuristic is costly, if you compute the heuristic for every node as soon as it is generated, you're spending a lot more time. This is a loser node. It will never really come to the front of the queue. Why do you care about its heuristic value? Okay, so you want another idea. So there was one idea I already told you for Llama, which is called multi-heuristic search. Okay, the other idea, and then in fact from FF there is another idea that we used called, what did I say that, enforced hill climbing. And then one more idea from FF is helpful actions, which we will talk about a little today. And Llama winds up using this idea also, and it calls it preferred operators. That means it reduces the branching factor. It doesn't include every action into the search tree at all. It will only include certain actions. Okay? And then that's from FF. And then additionally, these are all done in Llama 2. And Llama also does multi-heuristic search. And it also does delayed evaluation. What does delayed evaluation mean? You don't compute the heuristic of a node until it is actually picked up for expansion. So what happens? Do you guys see a problem with that?
How do you pick it for expansion?
Yeah, exactly. Yeah. So you use the proverb that what a fruit never falls too far from the tree. What is that proverb telling you? Your f value is not likely going to be much better than your parent's f value. So you would just make the node have its parent's f value and actually the parent's h value plus 1. Okay, as a placeholder. Obviously it's wrong. Okay, but then when you get picked up, then I will compute how good you are, and your children will inherit your real h value. And that's what delayed evaluation is. Now, these all look like hacks that people may have tried, when in 471 in Intro to AI, they wrote an A-star search algorithm and they started applying it to various problems. It's taking too long a time. You're trying any kind of a hack to improve the speed. They look like that, okay? And yet, these all actually have very significant impact on the performance of these planners, okay? And many of them actually are non-completeness preserving. This would not preserve completeness. This would not preserve completeness. This would not, no, this is okay actually. This definitely would not preserve completeness. That means when you pick a solution and stop, that won't be the optimal solution. So most of these ideas actually get used on the satisficing track. Okay, not on the optimizing track. Okay, now the reason I brought this up is you do need to understand these. Increasingly, in fact, in the community, people are coming up with theoretical reasons as to why those ideas actually make sense. Okay, they used to be not important enough. They look like hacks, so you just push it into the 59th page of the paper and sing, great praises of, relaxed plan heuristic. Now, Llama does it sort of halfway through, right? It actually calls itself Llama, landmark-based planner. Okay. And yet, in the paper itself, they do point out that its source of strength comes from all these things plus landmarks. In fact, all it does is one of these heuristics is relaxed plan, the other heuristic is landmarks. And there are two different queues. And you don't even know how often guys from the landmarks queue actually got picked. And in fact, there are reasons to believe that what is more important is to have two heuristics, not which are those two heuristics. Okay, so since it's a class, I can be upfront with you. It's not my paper anymore, so I can be upfront with you and tell you that even though I will give you some motherhood and apple pie, they may be just as believable as motherhood and apple pie. And there may be real reasons as to why these planners are working, and you need to be aware of the other reasons too. Okay? Questions? Okay. So, now having said that, now, I paid my lip service to this, now I will actually go with the motherhood and apple pie, which is relaxed plan heuristics, right? So if I'm doing relaxed plan heuristic, and assume that I'm doing A-star search, how do I use relaxed plan heuristic for progression versus regression search? That's a question, right? So for progression, obviously, what you wind up doing is, you start from the initial state, you have a bunch of states that you expanded, you expand the initial state, you got a bunch of new states. From each of these states, you have to compute an entire planning graph. until it levels off and the goals come in, then you find the relaxed plan in that and take the length of that. That will become the heuristic for this guy. And then one again here, one again here. So in progression, if you don't do delayed evaluation, which is what you normally, we assume that as soon as a node is generated, you compute its heuristic. In progression, you compute a planning graph for every one of these and compute the relaxed plan among that in each of those planning graphs. And these guys have a lot in common, but they're different. Do you see what I'm saying? So this guy has a whole bunch of state variables. Let's say there are 1000 state variables and they have, let's say, particular truth-falsity assignments. So 1 of 2 power 1000 assignments were true in the initial state. Now each of these would be 3 different other assignments. They will have enough in common because several of the variables might still be having the same values. To the extent we believe that actions change only a few variables at a time. And so there is a lot of commonality in the planning graph structure. But nevertheless, the simplest idea you can come up with is computing the planning graph separately for each of the states. Believe it or not, this is what FF does. So you were thinking, it's bad enough that planning graph heuristic is costly, but in some sense it is being done for each state. If on the other hand you're doing regression, remember there was a holy war between progression and regression, right? If on the other hand you're doing regression, what's interesting is planning graph is always grown from the initial state. So in the regression, initial state remains constant. This is your point of no change. Here basically planning graph is grown from the initial state, which is the floor, towards the ceiling, which is the goal state. In the progression, floor keeps changing and floor is raising until it reaches ceiling. So every time you need to compute, and then different parts of the floor are raising different heights. And so every time you have to compute for each of the states a different planning graph. In the regression on the other hand, the floor remains the same. Different pieces of ceiling are coming down. You guys remember stalagmites and stalagmites? Which is which, by the way? That's a trick question. You're supposed to know. I forgot already. But stalactites and stalagmites, one of which are going from bottom, one of which are coming from top. And there is some mnemonic for remembering which is which.
Stalactites are on top.
Stalactites are coming from down, right? So this is more of a stalactite search, right? Regression is a stalactite search. And progression is a stalagmite search. So each state is going to a different height, right? Then the question of course is, so because the floor is constant, you can just compute one planning graph and hang on to it. And anytime there is a new state, you check where that state appears in this planning graph. And suppose it appears here, then you compute the plan, relaxed plan for that state. So you just keep the same planning graph and recompute relaxed plans, different, each time you need it. So you save a huge amount because you are no longer going to recompute the planning graph. And this has nothing to do with just relaxed plan. Even if you are using set level heuristic or H sum, it's the same advantage. So regression only computes planning graph once, progression computes planning graph once for each node. So now who do you think should win, regression or progression? Right? We had some argument before, progression should be a loser, and because progression has a very large branching factor. But then we convinced ourselves that regression could be a loser too, because regression basically is really in 3 power n states rather than 2 power n states. And you don't know which are the dead states. Now I'm giving you another reason to kind of improve the regression's chances. It doesn't keep computing planning graphs everywhere. And for any of these planners, if you count the amount of time you spent in computing the heuristic versus the amount of time you spent in doing just child generation, which is the expansion phase, the heuristic, the current day heuristic planners spend most of their time actually doing heuristic computation. Okay, so the question then is, which one will win? What's your intuition? Regression should win. But is it winning? Have you been hearing a lot of buzz about regression? Right? So your intuition, comes to, comes and hits the reality, sad reality, which is regression still dies. Why? Because of the exact same reason. Progression, all it needs is, it knows that it's always in a consistent state. It just needs to know how many actions to get to the goal state. Regression, it doesn't really know whether these are consistent states or not. Now, if I'm using planning graph without mutual exclusions, will it tell me whether these are consistent or not? No, because I'm ignoring all the negative interactions. So if you ask the planning graph, give me a plan, this previous planning graph, give me a plan for supporting clear B and not clear B, do you think it will say, are you crazy? Or will it give you one? It will give you one. Right? It will say clear B and not clear B, so the clear B requires put down this thing and not clear B requires, let's say, this, and it add up those numbers and say 7 is the cost or 2 is the cost. And you basically pat yourself on the back and continue and then die, after about 18,000 levels. Because all the other children that you have produced are all dead. Okay? So, what that means essentially is that you don't expect relaxed planning graphs to particularly help regression planners. You need at least mutual exclusion information. And what really does happen is, because since we are getting into these exclusions in a minute, when you do introduce mutual exclusions, right, it does significantly improve the speed of the regression planners. So regression planners with normal relaxed plan versus regression planners with mutual exclusion relaxed plans, thus later do much better. Okay, and you would think that that should be a good combination, a comparison to progression. Unfortunately, even there it's still not enough. It does improve regression planners' performance significantly, but if your initial state doesn't have much of irrelevant stuff, progression still seems to dominate. Part of the reason to some extent is, actually we'll see that mutual exclusions, it's not enough to just compute binary mutual exclusions. If you really want to catch all the dying states, you need to compute ternary mutexes, quaternary mutexes, and that's much costlier. So you're doing one single planning graph, but lots and lots of analysis. Here, progression can do many planning graphs, but barely any analysis for any of them, because this just grows them, doesn't do any progression, any mutex computations. Okay? Questions? Okay. So this basically, whatever I said, it summarizes that. You can go back and read it. Okay? So interestingly, the heuristic was historically first used as progression, then they used it with the regression, then they found progression planners do better, then they found that combining them actually, that means if you combine mutexes, the regression does find better. We actually wrote a paper showing that if you do mutual exclusions with planning graphs, then in fact regression planners work better. That's what is used in the textbook. And then after that, people found that I avoided going into competitions because it's too much pain doing actual coding, and competitions actually have this advantage that you just compare entire packages. Okay, and it's a useful piece of additional information, and basically most of the competition winning planners have the progression standards. Okay, now that doesn't mean that regression will never have any use. It is that we still haven't figured out how to control the search for regression. Yes?
So one of the reasons it seems that regression tends to die is it can't tell you whether or not a particular regression step will reach an inconsistent state. Has anybody tried changing the structure of the planning graph rather than from using a bag of, fluents or values of fluents to actually represent a formula so you can check whether or not it's consistent?
So, variety of those sorts of things have been done, but none of them have worked. That doesn't necessarily mean that what you may be having in your mind won't work. Okay. In general, this label propagation, for example, the label propagation approaches use arbitrary propositional formulas as labels, and they define them as BDDs, and the conjunction and disjunction is over BDDs. So you actually get real propositional formulas. Okay, but that has been done, but that hasn't won the competition, for example. Okay. Now, there is a different point actually, that you can say. I mean, if you are into conspiracy theory and you decide this is your guy, and the competition is not being won by your guy, then you say that the competition is sort of weighed against your guy. Okay, so in fact, there is this idea that Will Cushing, one of my students, was actually talking about last year, and we tried. In fact, that's still open as a class project for somebody who might be interested. And it is this, which is, think of whether or not. So we compute. I mean, I'm doing this because A, in fact, it's a possible project idea and it's an open problem, and B, because there was a question. Okay. So the argument I gave as to why this dies and this doesn't die is this thing is always having consistent state, this one has inconsistent states. But I can look at it in a slightly different way. Just because you can make a move, next move, next move, next move, doesn't mean that you will reach somewhere. One particular way progression planners can die is that they made enough moves to paint themselves into a corner. Do you understand what I'm saying? Oh, so there is a grenade, I'll hold the grenade. There is a little cap for it, I'll open the cap. Now I've made 2 steps, I'm dead, essentially, right? This grenade is going off. It'll take 2 more steps and it's going to blow up on my face, right? I'm in a consistent state right now. I do have a full grenade, I'm a full person, but I'll still be dead 2 steps later. Okay? Why isn't that happening? It's supposed to happen in normal world. Okay? Why isn't it happening in benchmark domains? One reason is that we changed the world we live in. We made the worlds we live in to be largely ergodic. Ergodic means you never can paint yourself into a corner. Okay, I mean, with the kind of brains we have, and you know, especially the the new generations, the ones even younger than us have, you know, it's a surprise that they are not getting killed, you know, every 3 seconds, right? The reason they are not getting killed every 3 seconds is we made the life much more stable, and we used to start doing this, you know, we stabilize the environments first for our little kids, because kids they have no clue. I mean, if there's a nice little red thing, they'll put their hand on it. That happens to be a stove, so they'll essentially, you know, burn their hand. There'll be a big mirror-looking thing, they'll fall into it. That happens to be a swimming pool, right? So kids don't have that much of thinking, and still kids are not dying, except in Arizona and in summer. You know, mostly kids survive. Why? Because we put, you know, gates around swimming pools. We put kid inside a little, you know, enclosed surroundings, so that within that enclosed surroundings, it's an ergodic little enclosed surrounding. You know, they cannot actually paint themselves into a corner. So a question then is it really the progression and regression that are responsible for their respective advantages, or is it the domains over which you are essentially running the planners? Okay, if most domains you are running the planners, most benchmark domains you are running the planners are such that there are no traps in them, that means they are all completely ergodic, then you shouldn't be surprised that progression works well. So essentially, you know, one way of thinking about it is regression only knows that it will get here, but it doesn't know whether the path that it has traveled actually makes sense or not. To the extent this makes sense, it will get here. Progression, on the other hand, knows what it traveled is definitely going to make sense, but it has no clue whether it will reach actually the goal state. Okay, so they both have problems. However, the world is such that this guy's problem is not being exposed for what it is, because the one possible reason is that the domains are all ergodic. Now, how do you prove this? When you have a conspiracy theory that, you know, it's the mafia who killed Kennedy, right? I mean, how do we show this? So one way of showing this in this particular case is, suppose you were to take an arbitrary domain and time reverse it. Okay, remember, there is, given a domain, you can go planning progression, planning regression, with the domain remaining constant. But I can also change the domain such that in one domain time, you know, going forward means going backward in time. In another domain, going forward means going forward in time. Okay, so now I will have 4 combinations, right? I start with some real domain, I can understand in English. I can do the forward version, the backward version. Both of them have PDL formulas, I mean PDL actions, okay? And then you do D forward plus progression, D forward plus regression. And similarly, D backward plus progression, D backward plus regression. The idea then is, to the extent this is the natural way you would have written the domain, and progression is winning here, regression should win here, and vice versa. If so, then you can at least say that it's not the direction of the search that's killing you, it is the fact that the domain doesn't have any traps. Which could happen if you stabilized a part of the world. Whereas, if you take your robot to Mars, then there is no advance party to go before the robot to make sure that everything is stable and the robot won't fall off. In fact, many things that you understand in AI as very good ideas, you guys did game tree search, right? Like for example, in chess, if you see further, if you do limited depth look ahead, they say that the difference between the masters level player and an amateur player is a masters level player is effectively doing a 10-ply look ahead, maybe 12-ply look ahead. Okay, an amateur player is doing an 8-ply look ahead. That 2-ply extra makes all the difference. Now the effective depth of the full tree, that means finally all the leaf nodes in the game tree are either wins or losses. That's much, much larger. It's like 100 plus. And yet we are talking about 12 and 8 here. Why is that making so much of a difference? And in particular, actually one can argue that when you actually go deeper, there is much more noise you wind up considering, and so in fact your decision making should become less accurate, not more accurate. Okay, so it's very easy to construct, just as it's easy to construct domains where regression works well and progression works badly. It's also easy to construct games where deeper you look, the worse you do. And this idea is called game tree pathology. And this is what you would expect in boring games. But the games that people play have the property that they have traps. Chess is interesting exactly because you can lose the damn game in 3 moves. If you have no clue and I still have so many pieces, right? But my king can't move. He's just kind of squeezed to death. You can lose in like 3-4 moves. Do you understand what I'm saying? So in fact, what happens is that there is an analysis that Julia Pearl and other people have done many years back, that look ahead helps exactly when there is a certain fraction of trap positions. Otherwise, it's not supposed to work. Do you guys know any games that people play where there are no traps of this kind? Nim? I don't know what Nim is. I'm very bad with games. Actually, even chess I don't really know. But maybe Nim. I know one more name which also works. Go. Apparently, again, I could be completely wrong. Any of you know actually Go? Okay, this guy knows everything. Will Cushing also is crazy about it. He keeps going to these Go competitions. And Go is one of these things again where apparently traps are not that much. And it's not surprising that computer game players in Go are laughed out of the room by human players. Okay? So the reason I'm doing this is like a short 15-minute answer to that guy's question as to whether or not regression can ever be redeemed. I believe it can be by saying, you guys, regression won't work in IPC competitions where basically people very carefully generate domains which do not have traps. And if you don't have traps, this guy, the only thing he does badly, which is I don't know whether or not I'll ever reach the goal state, which it will not get that information by doing planning graph analysis, because planning graph might still say yes, 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 you can reach because you can do any action in parallel with any action. But it turns out you can't do certain actions in parallel with certain actions because of the negative interactions. And so in fact, unbeknownst to you, you actually just painted yourself into a corner. So for example, planning graph will say even if you have a grenade in your hand, you can just throw it out the window. Okay? But it might so happen that you are in a very small room and the window can't be opened in one step time frame. So you just sing a hymn and move on. Right? But the planning graph would not tell you that. It will still be very optimistic about your chances. It will say you'll still make it. You just have 2-3 steps to go. Okay? The point I'm trying to make is, why do we take this as just the way planning domains are? Why should we not get into traps? And you can make arguments both in favor of why the world is that way, because we design the world such that people less smarter than us can still survive in it. Okay? I mean, I'm being very modest here. So at least the world we design, it actually reduces the amount of crazy things that can happen to you, so it becomes effectively ergodic. Okay, but on the other hand, that's not the way the worlds are supposed to be necessarily. Okay? Any questions on this topic? Yes?
But since the goal state is partially specified and the initial state is fully specified, then aren't regression and regression only really equivalent if you're doing partially specified initial state?
Actually, so again, if you're into this, there is enough write-up on how to do this, how to set up this experiment, okay, such that you can actually convert a domain both. I mean, what you're saying is sort of relevant, but there are also other issues in terms of actually how do you just write the domain in 2 different directions. Given one domain in one direction, you can automatically generate time reverse domain from that. And then given a problem, you can solve it either which way. Okay? And I don't quite know whether what I'm alluding to will actually be borne out by these experiments. We sort of came up with these sort of experiments and identified a student to do it, and the student disappeared. And so, for various reasons. And so it hasn't been done. So you guys can do it. If one of you are interested enough in this, you can try it. And I will provide details. As I said, I do have about 8-9 ideas for possible class projects. Most of them would be about stuff I know, obviously. You can come up with your own ideas, or you can use one of my ideas. Okay, so this is one of them. I'll write about it. Okay. Okay.
Sir?
Yes, sir. Okay, as I'm doing this, you should see while I'm answering this guy's question, keep looking at the animation. It sort of shows what actually happens when a planning graph essentially winds up generating a planning graph. Progression winds up generating a planning graph for each of the nodes and generates the relaxed plan heuristic. One of my students generated this animation and he got PhD just for that, actually. Anyway, go ahead. Yeah.
Somewhere in this paper, they mentioned a technique called backward chaining.
Yeah.
So isn't that somewhat similar to regression?
Backward chaining and regression are different in the sense, in backward chaining, you don't necessarily construct goals. You don't necessarily construct states. You construct sub-goals. Okay? It's a very good point, and in fact, so right now these guys, all of them have different planning graphs, and each of them you have to compute the relaxed plan. And that's what you wind up doing for each. So there you go. So don't you think he deserves a PhD just for this? Anyway, so and as an answer to your question, in general, if there is any animation which is more than just things coming in, I didn't make it. Okay, so I copied it from somewhere. So suppose I have P, Q, and R. This is a good question, by the way. People should pay attention to him instead of the animation. He's asking the difference between regression and backchaining. Backchaining is a more generic term. Okay, regression is a very much more specific term, and you need to understand why the difference are. So suppose I do PQR and I do action A which gives P and requires M, right? Then what I will wind up getting in regression is I will basically say QRM. That's a regressed state. In the case of back chaining, on the other hand, you sort of effectively assume that even though you have the goal state to be PQR, you act as if they're all individual agents. P is required, Q is required, R is required. And so now actually A will say, oh, I'll give you P and I just require M. And then somebody else will say, I'll give you Q. This is A1, let's say, this is A, and let's say another A dash will say, I'll give you Q, I'll just require J. Now the interesting question is, unbeknownst to you, it may be the case that A dash will not only give Q, but will also remove P. And this picture doesn't tell you that information. And in backchaining is the way we tend to do goal-directed reasoning. Okay, so we'll say, oh, I need to be at home and I also need to have office hours. To be in office hours, I'll be in my office at some point of time. To be at home, I'll be in the car at some point of time. Now, if there's only one point of time left where I have to be both in the car as well as in the office, then I can't do it. Do you see what I'm saying? So backchaining essentially just does different lines separately. So it doesn't necessarily check whether or not there are going to be interactions in the state that comes up. Regression, on the other hand, doesn't allow you to have this wishy-washy big tree hanging about. It requires a state. And if you get this state, then you're done. Okay? Here on the other hand, even if I give you some way of making M true, some way of making J true, I may still not get P and Q. Right? Because A dash killed P. Okay, so backchaining is a more generic reasoning and regression is a much more specific reasoning. Now, interesting thing is backchaining underlies both regression and plan space planning. Okay, so the one partial order planning that you looked at, in essence, what would partial order planning have done in this case? It will say, okay, since A is giving P, so the picture, I'm going to remove this, and will say the picture in the partial order planning is, here is P, here is Q, here is R, here is A, A, and it gives P, so there is a link, P, and here is A dash, it gives Q, so there is a link Q, and these are part of the plan, and A dash still has a not P, and it has a J here, and it has a M here. These are the open conditions now. So partial order planning uses the same backchaining while keeping things reasonably separate, but still giving you soundness. Regression combines all the branches and gives you soundness. There are planners such as means ends analysis planners. The word strips in the strips representation comes from actually a package which had both the planner and the action representation thrown in. And the strips planner did means ends analysis plan. Okay, and means ends analysis again is based on the backward chaining idea, but the way it deals with the problems in backward chaining is hoping that it won't bite them. I mean that the problems won't happen. So what it does is it will essentially keep a stack of sub-goals. In the case of strips, you would just PQR, so you'll assume there is a stack of goals, P, Q and R. So I'll remove a goal and I'll put A here because A will give me P. And then so now Q will be M will be required for A. So then I'll work on M. Maybe some, A7 will give me M, but it will require W. Then I'll say, oh, the W is actually true in the initial state. So now this whole thing is done. Okay, so I can remove this whole thing and I'll assume now I'll only have to work on Q and R. Lovely idea. It looks like the stack of goals, you work on one goal at a time. Doesn't work in practice. And there are enough papers written to point out all sorts of problems with it. In particular, if you want to put a set of goals, if you want to put a set of n goals as a stack, how many different ways can you do that? N factorial ways. All you know is even if they're all workable, even if this problem can be solved, it only means that there exists some one of those n factorial permutations which would have worked. So strips has to basically, backtrack on all those orderings. In the good old days when strips were generated, by the way, you guys should read some really old papers on AI too, because it's good to know, how hard your life has become. In the original strips paper, which has probably 10,000 million citations, essentially the paper's contribution gets done in like the first 10 pages. And then the next, 70 pages or something, they say, here is our code. They'll write the whole code for you, When was the last time you actually read a paper where, unless you are in like a middle school or something and you're trying to impress your teacher that you know how to write code, here's the code for my program. Okay, so that's the way. So here is our code and it worked on these two problems. So what's wrong with you? Why are you giving us trouble? And then you submit it and then you'll get through, and then of course lots of people will find problems with it. Which is okay, that's the way science is supposed to happen. Okay, but in the context of mean sense analysis, backward chaining is a general sort of a meta idea. Backward chaining can be used as a regression, which is sound, as partial order planning, which is sound, as mean sense analysis, which is actually unsound. It's not just this n factorial. It turns out, you guys know Sussman anomaly, right? You heard the word Sussman anomaly. Somebody mentioned it in the notes. Yeah. So there is this thing called Sussman anomaly. And in a way it's kind of, for historical reasons, it's worth understanding what it is. Let me try to reconstruct it. Okay. Yeah, okay. So this is Sussman anomaly, I think. So from here, I believe you need to go to on AB and on BC. Go. Okay. So now what happens is, strips will consider all permutations of the goal orders, and if none of them work, it will just stop and say, I don't know what to do. Okay, so the question is, can I solve this problem by first working on AB completely, then working on BC from the state that comes from there, and concatenating those two plans. Okay, so to do on AB, what do I need to do? I basically put C down, put A here. That would be the plan. Okay, so I would be in this plan. And then from this state, if I do on BC, then I'll put A down, put B on top of this, and I'm done now. Unfortunately, I'm not done because on AB is gone. Now if I do the opposite, again the same problem, because if I do on BC first, then I put B on top of C. I'm done. Right? But then I have to undo that. And then I have to do on AB, by which time on BC is gone. So neither of the orders of the goals will work. So in particular, this is sort of, again, one more of the questions that led to this answer, which is that one interesting question is, people realize that strips may sometimes not be able to solve a planning problem. This idea of putting rows on the stack and considering all the orders and then just keep working on them one at a time would sometimes fail to solve problems. The question, of course, is what can you, if you're a computer scientist, you want to provide a simple characterization of those kinds of problems where strips will fail. Here is an example. This guy Sussman came up with this example just to show that strips will fail on this problem. It's a simple problem that will fail. And in general, strips will fail in any problem where the goals are not serializable. That means you can't work on one goal all the way, come to a state where that goal is true, and while keeping that goal true, you can achieve the next goal. If sub-goals are serializable, then this kind of a stack idea will work. But sometimes sub-goals are not serializable. So Sussman anomaly is a case where sub-goals are not serializable. Another example, classic example where sub-goals are not serializable is if I have two registers and a third register just hanging around. And this register has value 1, this register has value 2, I need to swap them. You all know that the only way to swap is basically take this guy, put it into that, then put this here, and then put this here. there is no way of achieving either one of the goals and then achieve the next goal. By the time you achieved one goal, you irretrievably lost the value that you need to keep. Now what's interesting is we don't talk about these problems anymore because it's not the search, it's not that they're hard problems, it is that the way you organized your search, the solution for that problem is not in your search space. Sussman anomaly problem is like very easy to solve for any of the, any planning problem. In fact, progression will solve it, regression will solve it, partial order planning will solve it. Only strips can't solve it. Okay. Now the reason why this stuff is actually interesting, even though it's all old and forgotten history, is that much of the analysis underlying landmarks is connected to serialization. Remember the connection of orderings between landmarks? What that means is this needs to be done first and then this. And then this needs to be done first and then this. Now even if there are serial chains, that doesn't necessarily mean that you know how to interleave those serial chains correctly, such that you'll get a full plan. So what landmark analysis with orderings tells you is something like this partially ordered plan. And if you start from there and actually do partial order planning, you're okay. Otherwise, you're only using it as a heuristic information. Any other questions? This is good stuff, by the way, this mean sense analysis connection. Especially if you ever talk to anybody from psychology who understands planning. They'll say humans do planning this way. But humans are also bozos. We just keep getting into trouble and redoing the plans. We are very bad at finding, reasonably optimal plans. Okay, so I have 10 minutes left. PGs for reducing actions, that's connected to the helpful actions heuristic. And the point about that is that if in fact, one of the interesting points is if I actually computed the planning graph up to level of, let's say, and certain actions didn't occur even in the last level, then I can be guaranteed that by not considering those actions in my search, I'm not losing anything. Right? Okay? And similarly, so if you just use the action instances at the final action level of the level planning graph, then you are guaranteed to preserve completeness. If these actions are only a subset of the total number of actions in the domain, and yet you are only considering a subset and doing better, and you're still keeping completeness. Now if you don't mind completeness and you want to be a little more reckless, then you can do this risky thing. If you are considering all the goals PQRS, just look at the actions that appear in the level preceding the first level where PQRS appear for the first time. Those, it's still not the level of, maybe some other actions would have come in, but the things that I'm interested in have already come in, so I'll only look at those actions. Now, if I only consider those actions pretty much at every level, then I'm likely to be complete, but I'll be definitely very efficient. An even more risky idea is to change the set of actions that I will consider from level to level. And so, for example, if I'm working, from this level and PQRS are present, right? So what I would wind up doing is that so I'm in this state from which I computed the planning graph, I found PQRS are present, I will compute the relaxed plan. Now, I'm right now in this state, right? Only consider the actions that are appearing in the first level of the relaxed plan. Not even the planning graph, just the relaxed plan. That's like really risky. It's like you're hoping that even if your relaxed plan is bogus, which you believe it is because it's ignoring negative interactions, at least its first level actions are non-bogus. This cuts down the number of actions you consider significantly. Right? You're only considering the actions that are present in the relaxed plan, not all the possible actions. And this is what's called the helpful actions heuristic. and then even more, I mean, so if in this case, basically what you consider is actions which are supporting PQRS goals. So the actions that appear in the first level of the relaxed plan that support the top level goals. Now if you want, you can generalize this idea to also work with landmark heuristics. So if you have landmarks, that means these are the final goals, but then there are this L1, L5, L9 that you also still have to work on. So you can consider the closest landmark from this state, find the relaxed plan for the closest landmark, look at only the actions that support that closest landmark. That's what is called preferred operators. And now of course, in the case of Llama, I mean, this is the journal paper that I sent you actually describes this idea. And to ensure, so one idea is, if this is like a big meta idea that you want to keep in mind, okay? If you don't know how to do things, and if you have a lot of ideas but you don't know whether the soundness preserving or not, throw them into the heuristic. Because heuristic doesn't hurt anybody. Okay? Search can actually go off in the wrong direction, and if in fact, and then declare victory like when there is no victory, actually. Heuristic will only push the search in the wrong direction, but no, if as long as the underlying search is complete, it can recover. Okay, so one idea that they do for the preferred operators is, remember I said they use multi-heuristics, there are 2 queues. Actually it's not 2 queues, they have like 10 queues. This is one bunch of queues for, this additional set of queues for where only the states that were reached using preferred operators are kept. So the idea then is, here is my state. Maybe these are all the actions A1 to A10 that will be relevant if you use FF's helpful action heuristic. Of these, only these A4, A5, A6 are relevant if you consider the closest landmark L1 and just find the relaxed plan for that. Llama would like to believe that these are more important than the rest of the actions. So what does it do? The states that you get by applying these actions, they are put in a, like a preferred queue. And you wind up expanding nodes from preferred queue more often than less preferred queues. And you can have a preferred queue for relaxed plan. I mean, so basically you can, this will then become something that just changes the heuristic, not the underlying plan. Okay? So that's the helpful actions heuristic. And as I said, it looks like it's not particularly, it looks like a hack, which it is to some extent, but it makes a huge difference in terms of performance. Okay? And in fact, there is a paper by Llama author Sylvia Reister and I think Malte Helmert, whose title is Preferred Operators and Deferred Evaluation. Looks like a really nice formal title, but what they're really saying is we'll give more importance to certain important operators, and we also avoid computing the heuristic until the node is picked up for expansion. That means we lose some accuracy.